All right, welcome to another meeting of New England Dynamics and Number Theory seminar. This time we're moving to New Jersey, and Han will introduce the speaker.
Okay. Hello, everybody. It's a great pleasure to introduce the speaker today, Chris Lutsko from Rutgers University. And the title of his talk is Paired Correlation of Monomial Sequences Modulo 1. So Chris, the floor is yours.
Okay, thank you very much. So thanks very much for the opportunity to speak. And let me also thank the organizers for this, for organizing this seminar. It's definitely one of the highlights of the week. So I'm going to talk about some recent work, which is joint with Athanasios Sourmelidis, who is at Graz, and Nicholas Technau, who recently moved to Caltech. And maybe I should start with an apology, because I know a lot of people are dynamicists, and I wish I could talk to you about horospherical equidistribution, but for whatever reason, the proofs went in another direction. So the proofs of our statements are pretty analytic number theory and flavor, but there's a lot of dynamics happening in the background. And so for that reason, I'm going to give more of a survey talk than a results talk. Okay. So what's the problem that we are concerned with? Well, throughout the talk, I'm going to fix an exponent theta, and I'm going to fix a dilation alpha. And now we're going to look at the sequence, which lives on the unit interval, alpha n to the theta, mod 1. Okay, so here n ranges over the natural numbers. Yeah, and so this is fixed for the rest of the talk. Just to get your intuitions going, here I've drawn the unit circle. So because of our mod 1 condition, we can identify 0 and 1. If I'm looking at the sequence alpha n, so here my exponent is 1, then we're talking about rotations by angle alpha. So we have 1 point here. This is alpha times 1. And then as n ranges through the integers, we pick up more and more points. All of these angles should be the same, but I've drawn them kind of badly, until we get all the way around the circle, and then we just keep going. As we keep going, we fill in the gaps, or in this case, if alpha is rational, then we'll eventually get a periodic orbit. So that's the case when the exponent is 1. If the exponent is larger than 1, again, you start off with just a rotation by alpha, but then your next rotation brings you to 4 alpha, and then 9 alpha, 16, 25. But then after that, you start filling in the gaps. So notice when the exponent is larger than 1, your points start getting more and more spaced apart, but the points on the unit circle eventually sort of fill up the space. Alternatively, you could have an exponent less than 1, in which case your points will sort of bunch up, like I've drawn here. But once you start going around the circle again, you start to fill in the gaps. Okay, so that's the setup. What's the question? Well, the question we want to ask, move this. Question we want to ask is, how do these points distribute on the unit circle? Slightly more specifically, we want to ask, when does this sequence look random in the limit as you take more and more points? And again, slightly more specifically, or mathematically speaking, we want to ask, what pseudo-random properties do these sequences satisfy? In other words, what properties do random sequences enjoy which are also satisfied by these deterministic sequences. Okay, now there's one example which I want to kind of set aside for this talk, because we're never going to find pseudo-random properties for this example. And that is, if my exponent theta is an integer and my my dilation alpha is rational, then this sequence, n to the theta times p over q mod 1, well, these are going to be fractions with denominator q. So now we're talking about modular arithmetic, and any of these pseudo-random properties are obviously not going to be satisfied. So for the purposes of this talk, this is a not so interesting example. Okay. So the obvious question here is, what do I mean by a sequence looking random? And there's several different measures which we can talk about. Perhaps the most natural starting point is what's called uniform distribution. So given a sequence xn, we say that xn is uniformly distributed on the unit interval. Everything I'm going to talk about today is with respect to Lebesgue measure, but it could be a different measure if you like. So it's uniformly distributed if, for any measurable subinterval, well, we're going to look at the proportion of points which lie in the interval I. We want that to converge to the measure of the interval. Okay, so anytime one of the xn's happens to fall into I, we pick up 1, and then we divide by the total number of points. So in a sense, this is measuring a global bias. You know, is there some set that these points avoid? Is there some set that these points are attracted to on a global scale? If you're a probabilist, then this is like a law of large numbers. So the question of uniform distribution has been more or less settled, and for these sequences. And this dates back to close to the turn of the century with the work of Weil. And he said that a sequence is uniformly distributed on the unit interval if and only if. Now, the actual Weil's criterion, you can get 3 or 4 different criteria, which are all equivalent, but I'm just going to select one. So a sequence is uniformly distributed if and only if I'm going to embed the sequence in the complex circle. So throughout the talk, e of x is going to be e to the 2 pi ix. So I look at how these points distribute on the complex circle. And then I want that average to converge to 0. But I'm also going to include a dilation k for any integer k. And for any integer k, I want that average to converge to 0. Okay. So this is, again, very natural. You're embedding these points on the complex circle, and you don't want there to be any bias in any particular direction, so that this average should converge to 0. The reason for the k is just to get rid of any rationality conditions. So for example, if my sequence was just 0, 1/2, 0, 1/2, then they would lie on opposite sides of the circle, and the average would of course converge to 0 as long as k is 1. But for k equals 2, this blows up. Okay. So this averaging on the complex circle is equivalent to uniform distribution. And using this plus a bit of Fourier analysis, Weil was able to have the following corollary. So again, now Now we're returning to the sequence xn is alpha n to the theta mod 1. And here, if theta is an integer, then xn is uniformly distributed as long as alpha is not rational. So as long as I'm not one of these sort of trivial cases that I highlighted earlier, then xn is going to be uniformly distributed. And if theta, if the exponent is not an integer, then xn is uniformly distributed for any value of alpha. Okay. Any questions so far? I should say, feel free to interrupt at any time. Okay.
Can I ask a question?
Yeah.
Yeah, just to make sure. So this chloride is due to Weil himself.
Yeah, this is in Weil's work. Yeah.
Yeah. Okay. Thanks.
Yeah. Okay. So the question of uniform distribution seems to be relatively settled for these sequences. You can talk about error terms if you like, but for the moment, let's set that aside. But in a sense, uniform distribution is not a fantastic measure of pseudo-randomness. It measures biases on a large scale, but there's plenty of sets which are definitely not randomly generated, which are visibly not randomly generated, but which are uniformly distributed. And I just want to highlight one example, which is the so-called three-gap theorem. So the three-gap theorem says, I'm going to look at alpha n mod 1. So this is the sequence of rotations that I had earlier. And I'm going to look at the gaps between neighboring elements. So on this picture, I have a gap here, I have a gap here, I have a gap here, etc. And the theorem says that if I write down all of these gaps, they're going to belong to a set of cardinality 3. So there's at most 3 different sized gaps at any time n. Of course, as you go later and later in the sequence, if alpha is irrational, the size of the gaps goes to 0. But nevertheless, at any point in time n, they fall into a set of size 3. So apparently this shows up in nature when you have the leaves of a plant apparently grow out with constant angle. So here the leaves or the petals of this flower are growing with angle, the golden angle. And these angles form a sequence. And the theorem states that the angle between here 1 and 9, 9 and 4, 4 and 7, these form the gaps, and the gaps fall into a set of size 3. So this was conjectured by the famous Polish mathematician Hugo Steinhaus, and then it was proved in the 1950s by Sourmelidis and Technau. And I should highlight that there's a very nice paper by Markov and Strombergson in 2017 where they were able to recover the three-gap theorem using homogeneous dynamics. So if that's more your flavor, then I would suggest that as some reading. But how does this fit into our narrative? Well, clearly these rotations are not random. They don't look random. They fail this fairly obvious test. So uniform distribution is a poor measure of pseudo-randomness on this kind of fine scale, on this finer scale. So this motivates the following definition, which is the gap distribution. So given a sequence xn on the unit interval, we're going to let un denote the ordered sequence at time capital N. So of course, the labeling of un secretly depends on capital N. So that's our ordered sequence. And now we're going to look at the following function. So we're going to look at the distance between un and its neighbor, un plus 1. And we're going to ask, when is that smaller than s over n? And then we want a proportion, so we divide by capital N. The reason for this capital N in the scaling here is, of course, if s is fixed, then your gaps are getting smaller and smaller, so you get more and more points which are close together. So we want to scale by the average gap size. So this is a function of s. And if this function Pn of s converges to P of s, then we call P the cumulative gap distribution. Okay, and if you take a derivative, you get the sort of regular gap distribution. Now,
so what's the meaning of this norm?
Mod 1.
Oh, norm mod 1.
Yeah, sorry. Whenever I
but they're all in the unit interval.
Yeah, but you could get 0.9 and
okay.
0.1. The distance there should be 0.2.
Okay, I see. Okay.
Thank you. Whenever I draw the two, whenever I draw a norm, it's going to mean mod 1. Okay, so that's our cumulative gap distribution. And now, when we talk about pseudo-random properties, well, we can talk about the gap distribution being Poissonian if P of s converges to the exponential distribution, so e to the minus s, which is what you would expect if you just had uniformly distributed random variables. So now the idea is we should start looking at the gap distribution, since this sort of gets around this issue raised by the 3-gap theorem. But this has a problem, which is analytically, it's very hard to order a sequence. At time capital N, it's hard to know who is neighbors with who. If you want a sort of mathematical explanation, we have to introduce a bunch of minima, and minima are hard to deal with analytically. Okay, so generally speaking, the gap distribution can be a very difficult problem for exactly this reason. There's no obvious ordering that we can get our hands on. So another measure of fine scale pseudo-randomness.
Can I ask a question about the previous slide about the Poisson gap? Are there any motivations for, why people would expect there will be Poissonian gap? Do you know any motivations for such a guess?
Well, it's essentially saying that the fine scale structure is not biased in any way. I'll get to some more concrete motivations later.
Yeah, thank you.
Okay, yeah. So another fine scale measure of pseudo-randomness that we can talk about is the so-called pair correlation. So now again, given my sequence, just a general sequence, I'm going to stop it at time n. We can define a function which takes an interval on the positive real line. And we're going to look at how many pairs, xi and xj, look at the distance between them and ask when does that lie in set I, and then we scale by a capital N so that our function doesn't blow up. And then, of course, we divide by capital N. So what you're asking is, given a point xi, what's the probability of finding another point nearby, xj? How much does the presence of a point tell you about the probability of finding another point nearby? Okay, so this is my pair correlation at time capital N. And if this pair correlation converges to the size of the interval for any measurable interval, then we say that the sequence has Poissonian pair correlation. Again, as you would expect for uniformly distributed random variables. Okay. Now, I want to make it clear that the pair correlation and the gap distribution are different measures of fine scale randomness. And it's not that one implies the other. These are independent measures of different properties. You can define higher level correlations, and at the very end of the talk, I will do so. And by the method of moments, if all of the correlations converge to, or if all of the correlations are Poissonian, then you get that the gap distribution is Poissonian. But again, the fact that all of the correlations are Poissonian is a stronger statement than the fact that the gap distribution is Poissonian. Okay. Okay, so for the purposes of today, the pair correlation is the central object which we're going to be studying. Now, a bit of motivation, and since this is a dynamics audience, I thought I'd take my motivation from dynamics, which is the study of quantum chaos. So we have these measures of pseudo-randomness on a fine scale. Who cares? Well, to explain this, I need to kind of tell a bit of a story, which is the story of quantum chaos. And this goes back to this dichotomy, which I'm sure we're all familiar with, which is integrable or chaotic systems. So if I have a billiard table, say I have a Bunimovich stadium, and I look at a typical trajectory, it's going to kind of go all over the place and look pretty random. Whereas if I have a square billiard, we're going to get this much more ordered trajectory. And this is the difference between integrable and chaotic dynamics. I don't really want to get into the definitions. If you're talking about a two-dimensional system, then an integrable system has an extra constraint on the dynamics. So here the momentum in the x direction, the momentum in the y direction are conserved, whereas here you have conservation of momentum and energy. Okay, so we've all seen these pictures of integrable and chaotic dynamics. Well, in the 1970s, mathematicians started to ask, is there a similar dichotomy in the quantum universe? So given, for example, a billiard table, we can consider the quantized dynamical system, which is just where you take the classical Hamiltonian and you replace it with a Schrodinger equation. And instead of having a particle, you have a wave function. So again, the question is, can we see this distinction between integrable and chaotic in the quantum system? Can we use the quantum system to kind of shed light on the dynamics in the classical system? Now, if you're studying quantum mechanics, one of the first things you do is you look for stationary solutions, which are characterized by energy levels, which means solving the Laplace eigenvalue problem. So Laplace phi equals energy level phi. So you want to look for eigenfunctions and eigenvalues which satisfy this equation. So if you do this and you stare at it long enough, you might come to the same conclusion as did Berry and Tabor, which is that integrable dynamics, if you have a generic integrable system, then the energy levels corresponding to the quantum system should have Poissonian local statistics. I don't really want to get into why they conjectured this. To be honest, we're sort of reaching the boundaries of my knowledge of quantum mechanics. But this is a sort of famous conjecture in this quantum chaos business. And so the idea is that this dichotomy is somehow determined by the local statistics of the energy levels. So Berry and Tabor, they said, great, now we just need to find some number theorists to tell us when does a system have Poissonian local statistics. And unfortunately, that seems to be a very difficult problem. There are very few examples where we actually know that a sequence has Poissonian local statistics. So one of the motivations for this project is to understand this question. When does any sequence have Poissonian local statistics? And hopefully one day we can go back to the physicists and give them their answer. Okay. Yeah, any questions about that? I know that was vague. There's fantastic lecture notes by Jens Markloff and also by Zeev Rudnick on this subject, which I can recommend. Okay, so that's our motivation. Okay. So what is known for our favorite sequence here, xn equals alpha n to the theta mod 1. I'm going to start with explicit results, and you'll see what that means in a second. And the first one we've already seen, it's the three-gap theorem. The three-gap theorem kind of tells you that the fine scale structure is not convergent. The gap distribution is never going to converge because it's too singular. So this example of rotations is kind of not so interesting for our purposes today. The other thing that's known for explicit sequences is this result by Elkies and McMullen, which says if I look at the sequence xn is alpha n to the 1/2 mod 1, and if alpha squared is rational, then xn has a gap distribution, so the gap distribution converges, but it's not Poissonian. And they do get an explicit gap distribution, and it's coming from homogeneous dynamics. So the point is that this sequence has exactly the right scaling for you to apply equidistribution of expanding horospheres, and then you can get some limiting distribution out of the other side. Now, 9 years later, Elbaz, Markloff, and Vinogradov, they were able to build on Elkies and McMullen's method, and they showed that in the same example, but now alpha here is 1. If I look at my sequence and I extract the squares, so that 1, 4, 9, 16, then this sequence does have Poissonian pair correlation. So this is this sort of odd example where you have a non-Poissonian gap distribution, but you do have a Poissonian pair correlation. Obviously, you have to extract the squares because otherwise you just get an accumulation at 0. You can extend this to alpha squared rational, but then you have to extract some condition that depends on alpha. Okay. So this is this kind of strange example where the scaling is exactly right in order to use homogeneous dynamics. And otherwise, if we're talking about explicit results, this is all that's known, essentially all that's known. There are some partial results, but this is really all that's known about convergence of the gap distribution and convergence of the pair correlation, at least to my knowledge. Now, in 1998, Rudnick and Sarnak decided, well, maybe we can, if we let alpha vary, then we can establish some metric results. So they were able to show that if theta is an integer, which isn't 1, then you do get Poissonian pair correlation for all alpha in a set of full measure. Now, what's nice here about if you're working in the metric situation is now you can start talking about trying to bound some variance. In other words, you've introduced an integral in alpha, and you can use some Fourier analysis to introduce an exponential. So now you have an integral of an exponential, which has nice cancellation properties. So that's where this proof is motivated. Some years later, Eisleitner, Elbaz, and Munch were able to extend this result to non-integer theta, as long as it's greater than 1. And then in the same year, Rudnick and Technau extended this to theta less than 1. But it's always using the same thing, which is variance bounds. These variance bounds won't hold if you're talking about the triple correlation. And there's no way to go from these metric results to more explicit results. But the metric question seems to be more or less resolved. The only other result which I'm going to mention is there's a result of Heath-Brown, which is for theta equals 2, where he gave a construction of a dense set of alpha for which xn has Poissonian pair correlation. However, his construction isn't sort of explicit. It doesn't tell you if you bring him a number, he can't tell you whether or not that dilation has Poissonian pair correlation. And essentially, that's the state of the art. There are some partial results, in particular when theta is 2, but otherwise not very much is known, especially if you want to say something for an explicit exponent and an explicit dilation. Okay, any questions? Great. Okay, so let me explain our main theorem, which you can find on the archive. So as long as theta is less than something slightly larger than a third, our sequence xn has Poissonian pair correlation for all values of alpha. So we're able to go beyond these metric results and actually say for any value of alpha, you get Poissonian pair correlation. Now, a few comments. We suspect that the theorem holds for theta less than 1/2, but there's a technical barrier, which I'll explain later, which is 14/41. I'd be thrilled if someone could extend that. But of course, the theorem doesn't hold for theta equals a half because of the squares, because of Elbad's, Markov, and Vinogradov's result. You have to remove the squares to get Poissonian pair correlation if alpha is 1. A kind of interesting example is that now if you look at n to the 1/3 mod 1, well, this is an example of a sequence which has Poissonian pair correlation, but which does not have Poissonian triple correlation, because the cubes get in the way exactly like the squares got in the way of n to the 1/2. So now we know for sure that this is an example of such a sequence, which I find kind of interesting. Okay, before I go on to the proof, any questions? Okay. Now the proof, as I kind of advertised, uses some more analytic techniques. So I'm going to briefly introduce those before getting to the proof. So the first analytic technique, which some of you are probably very familiar with, is Poisson summation. So if I have a sum of the function fn between a and b, well, that's equivalent to the integral of the function times e of kx. So in other words, it's equal to something that looks like a Fourier transform summed over all integers. If my sum here is over the integers, then really it is saying that sums over the integers are equivalent to sums over the integers of Fourier transforms. And there's an approximation sign because of boundary terms, which I don't want to get into. Okay. Now the second tool is slightly more involved, and it's called Van de Corput's B process. So what it says is, suppose I have a function which is nice, and the second derivative is roughly of size lambda for all x between capital A and capital B. Let little a be the derivative of phi at A, and let little b the derivative of phi at B. And now I'm going to look at the exponential sum, where I sum over e of phi of n for n ranging between a and b. And what this is saying is you can transform this sum. So you get a constant factor out front, which isn't very important. The sum is now over these little a's and little b's. In the denominator, I've pulled out a square root of the second derivative, and in the numerator, you transform the phase function. The phase here now depends on the unique solution to this equation. But the important thing is you transform the phase, and in the denominator, you pick up a square root of the second derivative. And then you get an error term. If you want to know where this comes from, well, we take our function e of phi of n, we apply Poisson summation, and we get sum over k e of phi of x minus kx. Now this is an oscillatory integral, so it looks something like this. And it has a stationary point at xn. And your integral is dominated by the behavior around here, which is what's happening in the numerator here. Okay, so this is a classic result from exponential sum theory. It's called the B process because there's also an A process. Fine. Okay, so what is a brief sketch of the proof? Well, I'm going to look at the smoothed pair correlation, which just says instead of looking for, okay, which says I take my difference of terms, alpha n1 to the theta minus alpha n2 to the theta, I periodize it with a k, I shrink it, I expand it with an n, and then I evaluate some function on that term. So if f was the indicator function of my interval I, then I would just recover the regular pair correlation as I stated it earlier. Okay, make sense? I haven't done anything but just smooth out the indicator function. And then we say, or it's equivalent to show that the pair correlation is Poissonian is equivalent to showing that the smooth pair correlation converges to the expectation of f for any f. Here, expectation just means integral. Okay. So that's our goal, is to show that R2 of f of n converges to expectation of f. We have this condition that n1 is not equal to n2. This is going to be kind of annoying, so we add it back in which case we want to show that R2 tilde converges to expectation of f plus the thing which we've added in, which turns out just to be an f of 0, right? If n1 equals n2, these guys both 0. For n large enough, the only term that contributes is k equals 0. So you pick up an n from here, it cancels with that one, and you get f of 0. Okay, so our goal is to show that R2 tilde converges to expectation of f plus f of 0. Let's apply Poisson summation to the sum over k. So here we have a sum over the integers. We can replace that with sum over the integers of the Fourier transform. So we pick up an f hat, k over n, and then we have this exponential sum. Notice that we've pulled out an n. Okay, so we've applied Poisson summation. Now we're going to pull out the term k equals 0. So here I should have this condition. And if you look at k equals 0, you get f hat of 0, which is exactly the expectation of f. So we've pulled out one of our main terms, and our goal is to show that this thing converges to f of 0 plus an error, which goes to 0. Okay, so we have this exponential phase, and we have our sums n1 and n2. So let's move the sum on the inside, and we get two exponential sums, which look like this. E of k is the sum, n goes from 1 to n, e k alpha n to the theta. We're going to hit this with the B process. We get a transformed phase. Here, capital theta is 1 over 1 minus little theta. Don't worry too much about that. You get some saving from the square root of the second derivative term. And you transform the phase. That's what you should be thinking. So now we have our transformed B process sums, and we get something that looks like this. Now our sums from n turned into sums over r. We pulled out this amplitude. We still have the sum over k, and we have a transformed phase in here. Now the last step is to take advantage of this sum over k. So if R1 equals R2, then the phase is 0, and you can use Riemann summation to show that you actually pick up f of 0. So now if R1 is not equal to R2, we have a phase, which depends on k, so hopefully we can get some cancellation from there. You can do partial summation, which means you can ignore this amplitude. You bring the k inside, and you're left with this exponential sum, where gamma here depends on R1 and R2. You do the B process to S, you get a little bit more saving, and then you hit it with an absolute values. It's important to remember that all of these steps up until now are involutions. We've done the B process, we've done partial summation, whatever. These are all involutions, and it's only now that we do the triangle inequality. Okay. So now you hit it with absolute values, and it turns out that the what you're left with is small O of 1. And this is enough to bring you all the way up to 1/3, and then you can do a little bit of technical work. Essentially, we need to take advantage of the remaining R sums in order to get past the third. So this uses van de Corput's A process, but I don't really want to get into that. Okay, any questions about the proof? Okay, so it's basically you do Fourier analysis to reduce everything to exponential sums, and then you hit stuff with the B process. You know, if all you have is a hammer, then every problem looks like a nail. Well, clearly one of us just read about the B process and decided to see where it would get us. Okay, moving on to some work in preparation. So we've been talking about the pair correlation. Well, you can also define the M-level correlation, which I alluded to earlier. If I'm given an interval I in R to the M minus 1, then I can define the M-level correlation. It's sort of analogous. You want xn1 minus xn2 to lie in I1, and you want xn2 minus xn3 to lie in I2, and this guy lies in IN minus 1. So you're asking, what's the probability if I have a point that there's another point nearby, and another point nearby that one, and another point nearby that one, etc., etc. So this is called the M-level correlation. And we say that a sequence has Poissonian M-level correlation if this function converges to the measure of the interval. And a theorem which is in preparation, we have the mathematics, we're sort of optimizing and writing, is that this sequence xn, which is alpha n to the theta mod 1, has Poissonian M-level correlations for all alpha greater than 0, provided theta is less than some upper bound. And we know that theta naught, this upper bound, goes to 0 as m goes to infinity. And the reason, again, is because n to the 1 over m does not have Poissonian M-level correlations. I can tell you that for the triple correlation, we can get this up to 1 over 13. I think with some extra work, we can get that all the way up to 1 over 11. And I'm sure somebody could do better. But that's where we are. Okay, let me stop there and open it up for questions. And I'm happy to expand on anything.
Yes, so, okay, sorry. Yeah, okay, I have a question, but maybe it's...
Yeah, we should thank the speaker first, right? Yeah.
So let me...
Okay, so are there any questions? So Dimitri, would you like to start?
I don't know, maybe somebody else. I just wanted to ask something I'm curious about, which is kind of steers it in different direction. So when I look at this setup of the problem, I kind of so in my mind it morphs into basically saying that you have approximation of alpha by rational numbers, but the denominators are crazy, right? So the denominators, you choose the denominators to be squares. Okay, and so that's kind of the setup that maybe is familiar to many people here. So the question is, do any methods that you're using say something about this kind of this strange form of metric theory of de Fontaine approximation, where you restrict the denominators and then they just come from some sequence.
Yeah, so
we can ask many questions. Probably, I understand that this is basically about pair correlations, but there are other stuff. So, for example, there is the work of Zaharescu, which I think was
sure. So
squared.
I think Diophantine conditions certainly come into play for larger values of the exponent. What we're kind of using here is this bunching up, which is kind of a crude behavior. For example, Rudnick and Sarnak, if you look at alpha n squared, they give Diophantine conditions on alpha for which this doesn't have Poissonian pair correlation.
Mm-hmm.
So there seems to be, it depends on the exponent, seems to be the answer. And we see that, for instance, with n to the 1/2, which is the most basic Diophantine condition, which is whether or not you're rational. So there is, I think that certainly comes into play, but our methods are kind of too crude to detect any Diophantine structure. It would be great if we could extend that, and it could be that combining that with exponential sum theory, combining Diophantine structure and rationality would give you much better bounds, and then you could prove convergence. But we're hitting this with some pretty crude hammers. Yeah, I don't know if that answers your question.
Yeah, I guess. So maybe one more question, which is kind of natural in this business. If you replace powers of n by primes, is anything known?
Primes to the power theta, you mean?
No, just a sequence of primes.
Oh, sequence of primes.
Do you have some correlation results or anything?
Not that I know of.
There is a result by Aled Walker in the metric setting for primes.
Okay.
He shows that they're not metric Poissonian. In other words, you don't get Poissonian pair correlations for almost every alpha if you take the integer sequence to be the primes.
So alpha times p.
Yeah, so if it's alpha times p.
Mod 1. Yeah.
Mm-hmm. Yeah, interesting. I didn't know about it. Okay, thanks.
Thank you.
Are there any other questions for our speaker?
I was going to ask whether anything is known if instead of on the circle, you take alpha to be a point, say, on a higher dimensional torus and consider the toral translation and the pair correlations. Is it somehow an easier problem there or different?
I don't know of anything in that direction. I haven't really thought about it.
Yeah. Okay, I guess that's all what we have today. Let's unmute ourselves and thank the speaker again.
You're welcome.
Okay, I'll see you. We'll see you next Thursday. Have a nice week.